Hello everyone, so in this video we are going to discuss about continuous time, unit step and unit impulse function. So in the previous video we have already discussed the discrete time unit step and unit impulse function. In this video we are going to discuss about the continuous time case. So we'll first define the continuous time unit step function. So it is defined as ut, which is equals to 0 when t is less than 0, and it will take a value of 1 when t is greater than 0. So to denote it graphically, we can plot a graph in which this axis represents the time axis. This point is t equal to 0 point, and the function will take a value of 1 if t is greater than 0, and will take a value of 0 if t is less than 0. So this is your ut. Important point to note here is that this function is discontinuous at t equal to 0. So this point we will discuss further. Next, we have seen that the unit impulse function and unit step function has a relationship between them. We can find one of the signal from the other signal. So as analogous to our discrete time case, we can have a relationship between the continuous time unit step and unit impulse function. So here we will first write the relationship between unit step function. So ut will be equal to minus infinity to t del of tau d tau. Here del tau represent your continuous time impulse function. So we can interpret this equation as the unit step signal is the running integral of our continuous time impulse signal, and this is analogous to a discrete time case where we said that u of n is equals to summation minus infinity to n del of m. So this was running sum, and here we are saying that this is running integral of our continuous time impulse function. Similarly, we can have a relationship for del of t, which is our unit impulse signal. So unit impulse signal is basically the first derivative of unit step function. So it can be written as del tau is equals to d of ut by dt. Now the expression looks simpler, but it has a difficulty which was not there in the case of discrete time. The difficulty is that, which I've already shown, that this function is discontinuous at t is equals to 0. This implies that the function will be non-differentiable. So it will be non-differentiable at t equal to 0. So how we can interpret this function? We have to make certain assumptions to interpret this equation. So we will assume that our ut is approximated as u of del of t. Here u del t has a different representation, so I'll show you by a graph. So this is our time axis and this is our del. So the graph of u del t will look like this. So in the case of unit impulse ut, the value was going from 0 to 1 instantaneously at t is equals to 0. But here what is happening, that it is taking a certain time delta to reach to a level of 1. So there is some finite slope involved in it, and this del is very short duration, so it is tending to 0. So how this helps is that when we take derivative of u delta t, then it will look like this. So we have a ramp function, so when we take a derivative of it, it will look like this. So this will be 0, this will be del, the time interval, and the amplitude will be 1 by delta. So this is the graph of u of delta t. So here again the delta is tending to 0. So if we interpret this function, this graph or del of t has a unit area also involved in it. So if we compute the area of this, then it will be 1 upon delta into delta, that will be equal to 1. So it is having a finite area of 1, but the duration is very short. So it is taking a value of 1 upon delta in a very short duration. So how it helps? So delta t is a short pulse of duration delta and with a unit area for any value of delta. And as the delta will tend to 0, delta t becomes narrower and narrower further. And it has to maintain its unit area. So its limiting form, so when we say that delta t will tend here, if we put the limit del tending to 0 delta t, it will be equivalent to your unit impulse signal. So the unit impulse signal is defined as limit del tending to 0, the approximate unit impulse signal, which was denoted by del of del t, and it has a unit area for any value of delta. So this is the interpretation for the unit impulse function, and this is quite different for the discrete time case. So how we can interpret if the like delta tends to 0, it is shown like an arrow at t equal to 0, and it has a value of 1. This 1 depicts not the value of this function, it depicts that the area is unit area. So it is depicting the area. So this is the representation of our del t function. Now again we can have the same property of sampling as we have seen in the discrete time case. So if we multiply our xt with this approximate unit impulse signal, we will get approximately the value of signal at x equal to 0 and multiplied with your impulse function. And again for del t, the delta should tend to 0, and what we get is our xt into impulse signal will equal to the value of the signal at x is equals to 0 multiplied with our impulse signal. And similarly, if we want to generalize this, we can have our xt multiplied with del of t minus t naught. So t naught can be any value. So what we'll get in output, we'll get the value of the signal at x of t naught multiplied with del function, which is del t minus t naught. So this is more generalized version of this sampling. So this is called the sampling property in continuous time case. So this is sampling property in continuous time case, and that is quite similar to that of the discrete time case. So this was all about the unit impulse signal and unit step function. Thanks.